Hi, my name is Leah Merritt, and today we're going to be learning about Kirschoff's rules. Kirschoff's first rule, the junction rule, applies the law of the conservation of charge. It states that the sum of all currents entering a junction must equal the sum of all currents leaving that same junction. Kirschoff's second rule, the loop rule, applies the law of the conservation of energy. It states that the algebraic sum of changes in potential around any closed circuit, path, or loop must be equal to 0. While Kirschoff's rules may not make a lot of sense just hearing them, it's important to understand them so that we can solve different problems pertaining to circuits and how current flows through them. First, let's talk about the junction rule. In this example, we have a junction right here. In one end comes the 15 amp current. Out of it comes a 10 amp current and a 5 amp current. We can see that this makes sense with the junction rule because the current flowing into the junction, 15 amps, is equal to the current coming out of the junction, 10 amps and 5 amps. If we put that into an equation, it would be I1 plus I2 equals I3 when I represents a current. In this case, it would be 5 amps plus 10 amps is equal to 15 amps. This second example can help us to understand the loop rule. This is a closed circuit with 3 resistors and 1 power source, or EMF. The EMF has a voltage potential of 10 volts. As we go around the circuit from the positive to the negative end of the EMF, the current will stay the same. However, the voltage will not stay the same because the potential energy, represented by volts, is being converted into other forms of energy by the resistors. At each resistor, we get what is called a voltage drop, where some of the voltage is lost before entering the next resistor. By the time we reach the negative end of the EMF again, the voltage will be at 0. This is the loop rule in action. If we want to put this into equation form, we can write out that the EMF minus the first resistor times the current minus the second resistor times the current minus the third resistor times the current is equal to 0. We can add over all the RIs to get that the EMF is equal to each resistor times the current added together. Note that there's only one current in this example because we only have one EMF and there are no junctions. If we plug in our numbers from this example, which is 10 volts and resistors of 2 ohms, 3 ohms, and 5 ohms, we get that 10 volts is equal to 2 ohms times I plus 3 ohms times I plus 5 ohms times I, which is equal to 10 ohms times I. When we divide over by the 10 ohms, we get that our current for this circuit is equal to 1 amp. So Kirschoff's law is especially helpful when we get into more complicated problems like this, where we have 2 different power sources, a couple of junctions, and we have 3 different currents because of these things. So in this problem, we actually have the 2 EMFs given to us, all the resistance values given to us, and then we need to find the currents. First, we need to start with the junction rule. If we say that this current coming out of the first EMF is called I3, and that this current coming out of the second EMF is called I1, and then the current in between these two, meeting them at the junction, is I2, then we have I1 plus I3 is equal to I2. So these 2 currents coming from the EMFs are equal to the current in the middle here. Now that we found the junction rule, we can use the loop rule to find the values more precisely. So when we're going around, we're going to pretend like we were doing what we did in the last problem, where we're just going straight in this loop from the positive end of the EMF to the negative end of the EMF, subtracting to equal 0. So EMF 1 minus the resistance 2. Now this time we multiply it by the second current, because that's the current that's running right here, minus the fourth resistor times the third current, because that's what current is running along here. That is all equal to 0. And then we're going to do the similar thing on this opposite current right here by saying that EMF 2 minus the third resistance times I2, because that's what current is running right here in the middle here, minus R2 times the first current, which is running through this second EMF here, minus R1 times that same I1. That's all equal to 0 as well. Then we can plug in any voltage values and ohm values that we've been given based on these EMFs and these resistors. And we get 10 minus 5I2 minus 20I3 is equal to 0, and 20 minus 5I2 minus 15I1 minus 10I1 is equal to 0. We can simplify these a little bit, and the best way to do this is that we can get I3 from this side. We can create an equation for I3, and then from this side over here, we can create an equation for I1. Then we can plug these equations for I3 and I1 into this first equation we derived, which is I1 plus I3 is equal to I2. So all of this is going to end up in terms of I2. And here we get 0.8 minus 0.2 I2 plus 0.5 minus 0.25 I2 is equal to I2. Now, if we do all the algebra involved with that, we will find that I2 is equal to 0.97a. And if we plug that I2 back into these equations for I3 and I1, we get that I1 is equal to 0.621 and I3 is equal to 0.672. All of those values are in amps. And we can check this work by adding these together, so I1 plus I3, and we will find that 0.621 plus 0.276 is actually equal to 0.897. That's all. Thanks for watching. Hi, my name is Leah Merritt, straight from the bits of